We have a topic that is geometrical meaning of this definite integral. What this definite integral means in geometry. So beta, without wasting the time, we are going to have its geometrical meaning. If I have this y-axis and this my x-axis, y-axis, and we know that this f of x, this is a function, and the function represents actually the curve. This function is actually the curve, and when the function is continuous, then it is the curve having no breaks. So here the function is continuous, so I will take this f of x, and we have this is continuous in AB, so here I will say A and I will take this B, because of from this point to this point the function is continuous. So here, if this is origin, then this is x is equal to A, and this will be x is equal to B. Now, the geometrical meaning of this very definite integral is that it represents, if we have an integral a to b and integral of this function f of x, this curve, then this geometrical meaning of this definite integral is that it gives us the area that is under this curve f of x bounded by this x is equal to a and x is equal to b and the x-axis. So the area that is inside this region is known to be the definite integral of f of x. So the f of x, so the definite integral of f of x is equal to the area of this. I can represent this A and this B, this C, and the area of A, B, C, D. So geometrically, the definite integral is the area bounded by the curve f of x and the bounds x is equal to A and x is equal to B and the x-axis. This is the geometrical interpretation of the definite integral. We are going to solve a beautiful result, that is, if we have a function f of x that is continuous in AB, like this, if I take the function f of x from A to B and it is continuous in this interval A to B from here to here, then the area bounded by the curve, that area which is bounded by the curve y is equal to fx, and the x-axis is this one, and the ordinates x is equal to A, x is equal to B, and this is equal to, that is equal to be the A to B f of x. What that means is, the statement says the area that is bounded by this curve and this line segment and this x-axis is equal to the definite integral of this function. So we are going to prove it, beta. You write down the statement first. You write, let f of x be continuous in AB, then the area bounded by the curve y is equal to f of x, comma, the x-axis and ordinates x is equal to A and x is equal to B is equal to A to B f of x dx. So now I am going to do its proof. The proof is very simple, but you have to keep full concentration here on board, and also I hope you must be very well known to the factors that are present in differential that we already discussed. So here I am going to give the proof. First, I will draw a graph. if this is my origin, this is my x-axis, this is my y-axis, and if this is my curve, okay, this is my curve y is equal to f of x, this is my bond, x is equal to a, and this one I take x is equal to b. So the distance from this origin to this point is a, and the distance from this origin to this point is b. So here it is my, if I will take this a, this one I will take b, this one I will take c, and this one I will take d. So now what I have to prove? I have to prove the area that is enclosed by this AD, this curve f of x, and these two bonds AB and DC, and this x-axis BC is equal to the integral of f of x. So I will write here first to prove जो हमें prove करना है, that is area of what? This A B C D is equal to integral of A to B, integral of A to B from this one to this one, f of x dr. This I have to prove. So I will write now prove. This theorem is very beautiful. It helps us to find the area under a curve. It is very useful, and it is also the application of the definite integral. You have to apply this theorem to your next unit, that is application of integral. There is only all the questions that are based on this formula. So now proof. We will take a point here, for example, P. So that the coordinates of this P are, we will take here, yes, P. We will take P here. So that this coordinates of this P are x and y. So I will take, let P x y be a point on curve. On curve y is equal to f of x. जो मेरी curve है उस पे मैं एक पॉइंट लेता हूँ जिसके कोऑर्डिनेट्स मैंने रखे, ऑर्डिनेट मैंने रखा वहां x एंड एब्सिसा मैंने रखा x एंड ऑर्डिनेट मैंने रखा y. Then from this point P, I will draw a perpendicular to this x-axis, for example PM. So I will write here and draw this PM perpendicular to x-axis. Let Px be the point on a curve y and draw PM perpendicular. Let the area that is this area below, this area, I will take this area equals to, for example, A. Let the area of this A, B, M, P, let area of A, P, B, M. So I am taking this portion of my region. So the area under the curve I am taking from that this portion, and I am taking its area as A. So now I have to find out the area that is from now this PM to DC. From this point P, first I will take another point Q. That's Q on this curve, and I know here my coordinates are P of x comma y. So I am going upside from this. I am going towards the right of this P. So I know that here both the coordinates that are first in P must have some number added. After that they can reach to this point. So I will take that distance from this point to this point. The distance of x-axis I will take that del x, and the increment of ordinate I will take by del y. So here I will take let q x plus del x comma y plus del y let this another point on y is equal to on the curve y is equal to f of x comma draw draw QN perpendicular again to BC. Draw QN perpendicular to axis. Again, first of all, you write here. First, I have taken this area A, B, M, P. I have taken this A. Now I will take the area this P, M, N, Q. The area that is under the curve of P, Q, and are bounded by this M, N, P, M, and Q, N. I will take that. And let area of this P, M, N, Q is equal to, I will take it equals to del A. So this is my equation first, and this one I take second equation. Now further draw PK perpendicular to this QN and QN perpendicular to extended portion of this PM. So I will take here. So I will this one K, this one I will represent a Z. So I have drawn this PK perpendicular to QN now, and this QZ I have drawn perpendicular to the extended portion of this PM, line segment PM. So here I will write again draw PQ perpendicular to MN, PK perpendicular to QN, and then this QZ I will draw perpendicular to this extended portion of P. Because I will say, yes, you write P Z, yeah, you will write this M Z now. So here, you write down this first. I'm going to erase it because here I cannot write here anything now. I have to go because it will not be seen to you. Okay. Now, now you see here, beta. The area this P M N K, the area of this rectangle P M N K. Can I say that this area is less than the area of P Q M N M? So I am saying that this area, the area that is from this P K to this M N, is less than the area from P Q to M N. So and the area P M N Q, this area, the area that is bounded by this region, is less than, can I say that the area M Z Q M? Yes, it is clearly getting answered by this graph. So I can say now, beta, now clearly area of this P K N M is less than area of, you check here, this P Q N M is less than area of Z M N Q. Z M N Q. Okay, I will erase these things. Only I will. These two equations. The first equation is area of this A, P, B. And only these things I will write. So now, which implies area of P, K, N, M. P, K, N, M is actually the area of the rectangle P, K, N, M. We know that area of a rectangle is length over breadth. But what is breadth here? The breadth is the distance from this M to M. We know that we have the coordinates of this P as X and Y. We take another point Q, the distance from this P to this Q, this line segment Q. We know that we have taken that by del X. So the distance from this point, that is del X, we are already get Y, because the coordinates of this are X plus del X. So if here is X, then here the point is X plus del X. So the distance that is from this point to this point is del X. So now our breadth is del X for the rectangle this PKM. What is the length? The length is actually the distance from this x-axis to this point. That is the coordinate y. What is the coordinate y here? That is equal to this. What is that equal to? Beta? Because the coordinates of this are x, comma y, and the coordinate y is equal to y. So length is our y. So length of this rectangle is y and breadth is del x. So area of this PKM, that is length of breadth, that will be y into del of x. This is my first, and then I have this thing less than area of PQNM. PQNM. that P, Q, and M I have taken as del A, it's the area. So I will write here, instead of this area, I will write this del A. So it will be del A. Okay, this is further less than area of Z, M, N, Q. Z, M, N, Q, which is again a rectangle, and we know that its area is length over breadth. The Z, Q, and M. Its area is length over breadth. Breadth is already del X, because we are again confined to this region. So breadth is del X. But what is length here? Length is actually the length of this PM plus from this point, that is Q, plus this PZ or this KZ, that is the total length, and we know that PM is actually Y, and this QZ is, we have taken it as Y plus del Y, so its length will be Y plus del Y. So here we know that the area is length over breadth. Length we have Y plus del Y, and breadth we have del X. So it is up to here understood. This one I will erase now, and now you have to remember here I have erased this. I hope you have written it. So here A, B, M, P, area A, B, M, P, I have taken it equal to A. This thing you have to. So now beta here I will divide throughout the del X. So here I will get Y del X divided by del X. Del X will get cancelled with del X, and less than, this is del A, and it will get divided by del X. This is less than Y plus del Y divided by del X, that will get cancelled. So I will take this equation forward. Now when del X turns to 0, that means when the distance, this del X, this Mn, or this Pk, or this Zq, when this will tend to 0, that means when this will shrink to 0, when the distance of del X Mn will shrink to 0, this N will come to this M, and this Q will come to this P. This K will come to this P. At that time, this KQ, the distance KQ, that was del Y. Del Y. When I will approach this N to this M, this Q will come to this P, and of course this KQ will tend to 0, because this distance will be no more than when this will become this line segment, and that KQ is actually the del Y. So when this del X turns to 0, which implies del Y tends to 0. Therefore, limit del X del Y turns to 0, this del A divided by del X, it will be equal to, by the differentiation you have already discussed there, that when we will give the del X turns to 0, del Y turns to 0, by the definition of derivative, and this will be equal to now d of A divided by d of X, derivative of A with respect to d of X. So these things you have to keep in consideration. Now I will erase this. This is a very beautiful theorem. Sorry, here it is, Y plus del A dot del X less than Y plus del Y. Now I will approach del X and del Y to 0 in this equation. So I will, which implies this, when I will give del X throughout, so what I will get when I will approach here del x and del y to 0. Here is not del x and del y, so y will be y. But we know that this when we are approaching the del x and del y to 0, the del x is getting equal to dA divided by dx. So here it will be dA divided by dx, and then less than, we are turning this del x and del y to 0. So here it will be del x turns to 0, del y turns to 0. When del y turns to 0, so here del y becomes 0, but y is y plus this del y will become 0. So now you can erase this. So what we got, y less than d by dx less than y plus 0, that is y. So here we got a situation that says the student here says this y is less than this dA by dx, but that is less than again y, and it is only possible when this dA divided by dx is actually equal to y. So I will write here, which implies dA divided by dx is equal to y. So this is my fourth equation. Now I will integrate on both sides this equation. So I will integrate on both sides with respect to x, but between the bonds, that's actually between the bonds, x is equal to a, y is equal to b. So therefore I will get here integral of a to b dA divided by dx, and then dx, I will get it equal to integral of a to b y dx. So we know that this integral and differential, they are inverse to each other, they will get cancelled out. So I will get here a but by the definition of fundamental theorem, it will be a between the bonds, this AB is equal to integral of, what is y? We know that y is f of x, so a to b f of x dx. I hope you write down this fast. We are taking it up. Hence we got this a to, we got this a to b is equal to integral of a to b f of x dx. Now you check here what this means is better. This means the value of this a at b minus the value of a at this point a. So it further means value of a at x is equal to b at x is equal to b minus value of a at x is equal to this point a is equal to this thing I am getting equal to the value of a at this x is equal to b minus value of a at x is equal to a. I am getting it equal to a to b f of x dx. What is actually a? A is the area under this curve, but from this point a p. So Here the question says value of A, that means the value of the area at x is equal to b, that means at x is equal to b, that is this point. So the area that is under this curve y is equal to fz and has bound this x is equal to b, that is equal to beta. Actually, if we have the perception of this thing, because we have taken this a b m p area, this equal to a. Now if we extend this area to this point, then we are getting this value of a at x is equal to b, we are getting it is equal to actually the area of a b c d. So this value will be equal to area of a b c d. Why? Because we have taken this a as the area of that is under the curve, this y is equal to fx, and have bonus this p m a b. But now we are extending this area by we are taking its value now from this point a b to this b, x is equal to b, and we are taking it the area under the curve y is equal to fx, and that is definitely equal to a b c this area. So minus. Now the second one says value of this, the value of the area at x is equal to a. This point, what is the area at this stage of this a? So a is the area is from this point to this. A I am taking from this to this. So when I will come back to this point, what is the area at that time? That is this. So after this, the area of this a is equal to nothing. It is just it is not the point a here. It is the area here. So the value of this a at this x is equal to a, that is 0. Why? Because I am taking a, the area from this region, the area that is from this region. So a, when I will shrink this area to the point a, then to this point x is equal to a, then it will be 0. It will be no. So this area will be 0. Is equal to a to b f of x dx. So here area of a b c d minus 0, that is nothing, and f of x dx hence proved. This is the geometrical representation of our definite integral. What? We got the area ABCD, that is the area under the curve y is equal to fx, and the bounds, and between the bounds x is equal to a and x is equal to b, and between this x-axis is equal to, we are getting that area equal to the definite integral of this curve. So this is the geometrical representation, and this is very beautiful theorem. You have to apply it in the next unit also, so you have to keep it under consideration in your memory. So you have to make lot of tries to this theorem so that you can easily do it by yourself after that. So now we are going to stop here. Tomorrow there will be another theorem that is based on the two results that we have already discussed, the definite integral as a limit of sum, and we know there are two formulas, limit as tends to 0, where limit as tends to 0 as into summation of something, and then as into summation of something. We are going to prove that very result also, but this is enough for today. Hope you have enjoyed this. Now